Hi again, Mrs. Hinano. I just wanted to break up your lecture this week into two. You might be able to just, listen to this towards the end when you're finishing up your notes for Unit 2. We're going to talk about historical research here also, and we're going to talk about ways to do science. We're going to talk about, sorry, can't do two things at once. We're going to talk about research methods. What I really want you to focus on with this is I want you to focus on major things like how we collect data, like case studies, surveys, experiments, naturalistic observation. Those are big on the psychology test. What's also big on psychology test, which we are going to talk about next week's lecture, not this week's lecture, is how to analyze the data, even though you're going to be reading on that. So when you read your textbooks this week, be sure that you are focusing on scatter plots and mean, median modes and how to interpret it and correlation bias and all of that stuff. But for this lecture, we're going to merely focus on linking how we collect data with your graded discussion that I want you to have when it comes to trying to prove nature versus nurture. What experiment would you use in order to try to prove that? And then next week, we're going to talk about how we could have possibly errors in those as we try to prove them. So let's go to the parts of the lecture that I want you to really think of. Now, we're going to jump around a little bit. So just bear with me. It'll make sense when we're done. So we're talking about research methods. And the big question is how do we separate opinion from science? Because everybody has a ton of opinions when it comes to psychology. Like, in my opinion, violent video games are not bad. Well, I'm really glad that you have that opinion, but it's still an opinion, and your opinion, I hate to say it, is kind of irrelevant when we do science. And getting to the point where we actually realize that opinions are irrelevant when we talk about science is really, really tough, especially in the United States, because everybody loves to have an opinion. You might want to think that violent video games do no harm, but the science might prove you wrong. And if the science proves you wrong, then your opinion is still your opinion, but it's not based in science. And that's a big, big difference. So basically, scientific theory is not your everyday theory. And so, like, I have a theory on why it's sunny today. And my theory on why it's sunny today is because it was cloudy yesterday. That's like a theory that we use in everyday life. It's not a scientific theory. A scientific theory explains through an integrated set of principles that organizes observations and predicted behaviors or events after years and years and years and years of scientific experimentation, review, and replication. So if you have a scientific theory, it is not a theory like, hey, I have a theory of if you walk under a ladder, it'll bring bad luck. That's a superstition, and we throw the word theory around all the time. The word scientific theory is totally different than our everyday use of theory. This is comes to fruition after years, and I'm talking like decades, 20 years, 30 years, 50 years of experimentation, review of that theory, replication, and you seem to have the same findings every time. But the big problem is that our brains don't think like that. Our brains are not naturally scientific thinkers, so sometimes we have to trick our brains into thinking this way, and sometimes our intuition is wrong. So these are a couple riddles. I want you to read them over, see if you can get them right. I'll tell you the answers in a couple minutes. So if you drop a ball or drop a bullet off a table 3 feet high and fire one across the football field, which one hits the ground first? If you guys have taken a physics class, you're going to get the answers. A ball rolls down a spiral track. At the end of the track, it curves left. What path does it take when it leaves the track? A wooden cube is 1 inch long on each side. How many cubes for a 2-inch long cube? Oh, I probably should give you the answers, shouldn't I? Well, the bullet one should be kind of easy because of gravity, right? Gravity happens at the same velocity or at the same pressure regardless of the velocity and regardless of whether something is moving. So they touch the ground at the exact same time. It's hard for us to think that a bullet flying through the air really, really fast would touch the ground at the same time of if I just dropped it. But that's physics and science. Number 2, we want to say it goes left, but it doesn't. It goes straight. The only thing that's taking the ball left is the spiral track. Okay. Oops, I need to change that misspelling. Sorry, there's a T there, and it should be a K. Okay, wooden cube, you're cubing something. So yeah, it changes the answers. It's not 4, it's 8. So we have to be careful of our brain because sometimes our brain does not work well. We're going to come back and talk about all of the biases that we have out there. That's going to be week 3 lecture because I'm going to take a lot more time on that. And I am going to talk to you about correlation and all of that stuff. But what I do want to talk to you this time is about the 3 most important attitudes to have when you're doing science. The first one is that we must be curious. So as soon as we find an answer in science, we can't say, okay, done, case closed. We're going to, wipe our hands and be done with it. We have to be curious and ask why questions. I just took a grad class, and it was really interesting, and the professor forced us to ask 5 why questions before we could answer the question. So irritating, but so important because, especially to the scientific method, it's like, I don't want to ask another why question. And he'd be always like, have you reached your 5 why questions? And I'd be like, no. And so it just gets you really, really deeper into the subject matter when you ask the 5 why questions. And so be curious, investigate, be inquisitive, meddlesome why questions all the time are helpful. The next thing is skeptical. Now, we have to be skeptical about skepticism because there is Lola. Sorry, that's Lola. There is skepticism, and then there's denial. And so I think that a healthy skepticism, quizzical, disbelieving, being leery of the way the world works is important in science. But once science is replicated for 30 years and you're still scoffing, as it says up here, to the concept of global warming, you have gone beyond skeptical. You have gone to just denial. And so when, I would argue when you get to the point of like 99% of all scientists agree, your skepticism, if you're still skeptical of the results, has turned into, I just don't feel like believing it. And so be careful of that. Be skeptical, but don't be in a state of denial of, what is common understanding of science. So, another example is like there are people that are skeptical on whether the world is actually round. Yeah, it's a real thing. You should look it up. It's a pretty cool video. Vsauce, if you don't watch Vsauce, watch Vsauce. It's so much fun. And he does a thing on what would actually have to happen to gravity if the world was flat. And so he kind of unequivocally proves that the world is round. But yeah, there are people that believe maybe the world really is flat. And so he pretty much debunks that because gravity would do some really crazy things if the world was flat. Also be humble. So I guess this comes to skepticism also. So when science does change, let's just say that global warming is actually a hoax and 99% of the scientists are wrong and the 1% of the scientists that believe it's not really happening are right. What happens when the 1% is proven right? Well, the responsible scientists acknowledge, you know what? We were in the majority. It was 99%. Right, that we thought it was this way, but you are actually right and you proved us wrong and you have replicable science to prove it. Okay, so we have to be willing to say that we were wrong. We have to be willing to say, you know what, we thought the world was round, but now it's flat, if science proved it that way. Okay, so I'm not quite convinced that the science will prove the global warming. You know, this is just, I default to the majority of scientists. I think you should know that about me right away. If like, you know, 80, 85, 90% of scientists out there say something, I'm usually going to default to them. I can still be like, hey, did they do their science right? But just simply sweepingly denying stuff because we can't prove it 100%, I think is irresponsible. But you still have to be humble when somebody proves you're right. So basically the scientific community is a humble community that scrutinizes competing ideas. So we have to have these competing ideas. We have to have people that question us. But we also have to have a sense of, you know what, at some point in time we have to move forward because the overwhelming majority believes in this way. Okay, so what I'm asking for you to do is to think critically about everything. Be a critical thinker just in general, but don't be a conspiratorial thinker. I think there's a fine line between that. We are not going to go over this right yet. We're going to come back to this. What I really want to look at here is the scientific method of psychology. So this is a great visual to kind of analyze the cycle of the scientific theory. And for many of you who have taken lots of advanced science classes, this is simply review for you. But obviously we start with a theory, which is a set of principles organized our observations, predictions, behaviors, linking fact and meaning together. And we've got this theory. And so in order to prove this theory, we have to, you know, hypothesize. So every good theory is testable. So we have the theory of gravity. Actually, it's a law, isn't it? Newton's law of gravity, yeah. But we have a theory of evolution. Every good theory is predictable. So we have a question, okay? We want to question whether the theory of evolution is actually a thing. So let's say we question it and we're gonna say, okay, I'm gonna look at the brain as an example of evolution. And you're going to create questions that would attempt to get you closer at the answer to prove the theory of evolution through the brain. Maybe I would say I'm going to dissect a dog's brain, a cat's brain, a human brain, and see if there's any commonalities there so I can deduct the fact that, you know, we've evolved from the same organism because of the similar brain structures that we have. It could be a question. I think it is a question, and I think that's what biologists do, but I am not a biologist. When you have these hypotheses and you're questioning your theories, beware of your biases in your questions. Just be wary that we are all human beings and we all have biases. So let's say we have a theory that violent video games perpetuates violence in young kids. My bias might be that I am an engineer of violent video games and I want to create some scientific methods and scientific theory that will prove that what I'm doing is doing no harm. Yeah, you really can't do that because you are obviously monetarily invested into the science that you are trying to do. You need to have a non-biased outsider observe your industry to make those conclusions. The next thing that we can talk about is operationalization. So operationalization, I think I said that right. So this is a process of making the fuzzy clear and measurable. So we have to have operational definitions. Please know this in your textbook. They talk about operational definitions. I would argue one of the most important but often skipped processes in the scientific method. You have to define everything in the scientific method. Like, so if you're going to say something is excellent, you need to define excellent, okay? Which is not very scientific. It's a bad example, I'm sorry, but let's say you're going to try to predict if looking at the ground causes pessimistic views, which tend to be present in depressed people that struggle with depression, okay? So you have to define what it means to look to the ground. Like, how often are you looking at the ground? Are you looking at the ground 100% of the time when you walk? Or are you looking at it 50% of the time you walk? or looking at the ground means, you know, below the horizon, or looking at the ground can be looking straight ahead and below. It can get really dicey when it comes to operationalization. So you want to make sure that when you do your study, it can be replicated. And the only way to replicate it is to make sure that you define everything so that they can do the exact same study again and again and again. The next stop in the scientific theory, or next part of the scientific theory, would be design of the study. So clearly define and explain what you're doing, your plans for exploration. How are you going to get the data? Are you going to do a case study? Are you going to do a survey? Are you going to do a naturalistic observation? Or are you going to do an experiment? How are you going to have a control group? How are you going to have a representative population? Is it going to be randomly selected? Et cetera, et cetera. For any of these, mostly what I listed off there was about experiments and surveys with random sampling and control groups. But case studies are interesting. We love to use case studies to prove stuff in psychology, and we have to be very, very careful of finding one person that had something really weird happen to the brain and say, hey, this is how the brain works, because that could be unique to simply one person. The next step is the analysis of the data. So you have to find correlation and the correlation coefficient. You have to use scatter plots, causation, illusionary correlation, biases. We haven't talked about the biases yet, but read up on this in your unit because the analysis of data is key. We cannot find correlation or causation where none exist. And there is a big difference between correlation and causation. Correlation means that it just happened to happen at the same time. It could be a complete and total coincidence that it happened at the same time. And that's literally has to be said in the science. Causation says that this contributed to that, okay? So, for example, let's go back to our violent video game example. Let's say we are going to try to prove that violent video games cause children to be violent, okay? There's a big key between correlation and causation. So there could be a correlation between kids acting out violently and watching violent video games, but you have to decipher all of the variables that go into that. So is it just a correlation because those children happen to be raised in families that don't find violence that big of a deal, and so maybe their family's a little bit more violent? Maybe they have rough and tumble siblings. They have a lot of them. They tend to wrestle a lot. They tend to resolve conflict with, you know, just boys in the backyard working it out, and their dad seems to advocate for that. Plus, they also embrace violent video games. How are you going to decide which one is causing the violent behavior? The culture of the family or the use of the video games, because those could be happening at the exact same time. So it could just be a correlation there. Causation is very different. You'd have to prove that the actual video game is what is actually causing the violence, and that is so hard, and that's why all of the evidence is really being worked through with that issue. We just simply do not know. For as many surveys I could find that say violent video games cause violent behaviors, I can find studies and surveys and experiments that say the exact opposite. So the data is really, really murky still, and the science is still really young when it comes to that. So good news, you can still play Fallout, right? The interpretation of data is another thing. So like, how do we measure central tendency, variations, interference, statistical significance? All of this stuff is emphasized in your textbook. Please know all of the vocabulary. Again, not for this week, but next week when I have you dive into the stats more, and that discussion, is that going to be important? And I want you just to see the broad definition of scientific theory today in this week, and not just the specifics. And next week we'll go back to the specifics of Unit 2. And then implications for theory. This enables us to test, reject, revise, revisit, rethink in a new direction. And then if replication is the main goal, we're going to replicate it. And if we get the same stuff over and over again, then we can say, you know what, it's a pretty good theory. If we get different stuff, then we're going to have to change our theory. Okay, so hopefully that helps with, whoops, we don't want to go there. Hopefully that helps with what I want to do this week when it comes to your case study. So this is what I want down here. Sorry, I jumped around like that. So here I want you to have a little brief discussion on what would be the pros and cons of a case study, pros and cons of a survey, pros and cons of naturalistic observation, and pros and cons of experimentation. So for discussion, week 2, you are going to do 3 things. It is complicated. Let's go to the discussion boards, and we will clearly explain it here as soon as I thought it. Sorry, I thought I was logged in. Week 2 discussion boards. Well, that was quick. So step 1, using your notes. I need to have evidence of those notes, readings, and attached picture, which I did from the Prezi. Okay, pick one approach. What are the approaches? The approaches are the picture attached, which was right here. Biological approach, evolutionary approach, psychoanalysis approach, cognitive, humanistic, sociocultural behavior. So your first step is to pick an approach. Okay. Number 1 says define the approach in your own words. So read the approach in your textbook, define it in your own words. If it helps you in the discussion post, you can actually put a number 1, define your approach. Okay. Then find your approach, find the appropriate thread and answer the following questions and create an argument. So link your approach to nature versus nurture spectrum. Justify why you believe this. So this is your thread. How does science help you prove your approach is best? What scientific method would you employ when you're studying psychology from this approach? So when I say scientific methods, I mean, would you pick a case study? Would you pick an experiment? Would you pick a survey? Or would you pick a naturalistic observation? And then I want you to create an argument for nature versus nurture using this approach and proving that you could prove your opinion or your scientific theory about nature versus nurture using the experimentation. Okay? Step 2, on 2 different threads. You're going to read classmates. You're going to respond with how are your approaches similar and different? And do you still believe that your approach is the same? Okay? Sorry, my dog is barking right now. I hope you can hear me well. Okay? Hopefully we understand this. Okay? You're going to define your approach. You're going to link it to nature versus nurture. You're going to how would science help you prove it? And then you're going to try to create an argument. You don't actually have to create the scientific method, but create an argument arguing that, yes, I can prove that we are products of our social environment, nurture, or we are products of our DNA and biology. Okay? Again, I want you to message me on Schoology if you have any questions about this. Okay, it's a little bit more complicated than last week, but you guys nailed last week, so I think you can for sure handle it. Okay, hope we have another great week. Thanks, everyone.